In this video, we're going to look at a series question. So it says, write the first four non-zero terms and the general term for the Taylor series. Okay, so f was this function, and of course a Taylor series about x equals 0 is nice because it's actually a Maclaurin series, and of course we know e to the x. So down here, let me start with a. So f of x is e to the negative x squared. So over here, let me just remind you that e to the x is approximated by 1 plus x squared over 2 factorial plus x cubed. So this is the Maclaurin series. It's x to the n over n factorial. Well, this is e to the negative x squared. So every time we had an x, we're going to make it a negative x squared. So it's going to be 1 plus negative x squared plus negative x squared squared plus negative x squared cubed, like that. And they also want the general term, so of course that's going to be negative x squared to the n over n factorial. Well, we can clean this up a little bit. We'd have 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. And the general term would be negative x to the 2n over n factorial, something like that. Okay? So part B says use that answer to find the limit as x approaches 0 of 1 minus x squared minus f of x over x to the 4th. So, let's, and of course, if you think about f of x, at 0 it'd be 1 minus x squared minus the function. Let me even put that up here. We've got the limit as x approaches 0 of 1 minus x squared minus e to the negative x squared all over x to the 4th. So what we're going to do is we're going to replace our or the f of x with our series, okay, because they wanted us to use our series. So we're going to have 1 minus x squared minus, and I'm going to put my terms in, okay, from right here, these terms. So 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. And I'm dividing the entire thing by x to the 4th. Well, let's clean this up a little bit. Maybe let me go up here so I get a little more room. So 1 minus x squared minus 1 plus x squared minus x to the 4th over 2 factorial plus x to the 6th over 3 factorial. And we're dividing all of it by x to the 4th. Well, let's cross out some things because these and these are 0. So then we've got x to the 4th over 2 negative x to the 4th over 2 factorial divided by x to the 4th. That's just negative 1 over 2 factorial. And x to the 6th divided by, this would be x squared over 3 factorial. So if I take the limit as x approaches 0 of this, because that's what we're trying to do, is evaluate the limit as x approach 0, this is negative 1/2. And I'm done. Okay, so this is something that's been really common, using a series and then replacing it in a function. And this function would be hard to analyze. Think about, you get 0 over 0. So then you think, okay, well, I'll do L'Hopital. Yeah, but you need to use L'Hopital quite a few times to pull this down. And you need to use L'Hopital as many times up here. And, of course, the derivative is 0 minus 2x. And then this thing, you'd have to use chain rule, but the next time you do the derivative, you'd need product rule. So it would really be a hassle to evaluate that limit because of you'd need to do L'Hopital multiple times involving quite a bit of product rule and chain rule. And if I simply replace f of x with what I have said f of x is approximately equivalent to, it's almost the same as this, then I can just clean up, simplify, and plug 0 in like I'd normally like to do a limit. I get negative 1/2 plus 0, so negative 1/2 is the limit. All right, let's do part C. So it says, write the first 4 non-zero terms for the integral. Okay, well, let's just remind ourselves that we thought f of x, e to the negative x squared, was approximately 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. So that's what we had for part A. So now we want to integrate it. So let's do that. Let's find the antiderivative. And remember, it's term by term. So, and that's how we do polynomials. If I want to integrate this, I simply find the antiderivative of each term. So we got x minus 1/3 x cubed plus 1 over 5 times 2 factorial, so that 2 factorial was already there, x to the 5th, and here we raise the power, so 7 times 3 factorial, x to the 7th. Okay, and it says use the first 2 terms to estimate the area from 0 to 1/2. So we're just going to use these 2 terms. This is the antiderivative. So we'd have x minus 1/3 x cubed evaluated at 1/2 and 0. Well, if I plug in 1/2, I get 1/2 minus 1/3 times 1/2 cubed, which is the same as 1/2 minus 1/3 times 1/8, which is 1/2 minus 1/24, which is 11/24. Okay, there that is. All right, so now, and of course if I plug in 0, I get 0. That's why I only plugged in the top bound. Part D says, explain why that estimate is differing from the actual value by less than 1/200th. Well, important to realize that, and you should state, the series is alternating, so that's great because that means that we don't have to do Lagrange error bound. We can simply look at the next term. So we go to the next term. Let me put a big circle around here. Here's the first term we didn't use. Okay, so next term right here. And we simply plug 1/2 into that. Okay, because we plugged 1/2, into these two. So now we plug 1/2 into this. So we have 1 over 5 times 2 factorial times 1/2 to the 5th power. Well, this is 1/10 times, and think 2 times 2 is 4, times 2 is 8, times 2 is 16. This is 1/32, that 1/2 to the 5th. Well, this is 1 over 320, and that is definitely less than 1/200th. So our error bound is such that we are within 1/320th, which is definitely satisfying what they tell us we need to be within. Okay, so this is just kind of a standard a series question. You got to make a series, then use it. A couple of ways that are really useful, to evaluate a limit and to evaluate an integral that would have been impossible with the methods we know. We wouldn't have known how to integrate this by hand. And then we got to use some error bound, which is always useful. If you make an approximation, it's good to know how close you are, and we did that. So this kind of covers all of the major things with series.